Advance the slide, go back. Advance forward, back.
Okay.
All right, why don't we go ahead and get started? Welcome back, everyone. We're gonna do some really exciting stuff now. We're gonna go through all the teams, and they're gonna tell us about what they've been up to over the past couple of days, what results they have. So yeah, we'll start with team number one. Please take it away.
Hi, everyone. Can you hear me? Great. So our team decided to work on the first project for occurrence rates. So we were interested to see how combining different surveys led to different occurrence measurements.
Sweet, thank you. So the question we need to ask ourselves is, why would we want to combine different surveys? And I'm glad that we just had an entire week of talking about why we would need to do that. No one survey is perfect. They all cover different parts of parameter space. They all have their strengths and weaknesses. And so if we want to maximize our information and maximize the coverage that we have, we are going to have to combine multiple survey types. But of course, this comes with a lot of issues. And so I think that we need to approach it with a lot of caution, right? Different surveys have different completeness, different biases. And I kind of think of it almost like we're chefs, right? And we're making some cake or dinner or something. You have to be very careful with these different ingredients. If you are misusing them, if you're not following the recipe, there's a very high chance that things are going to go wrong. And so much caution is needed. And I think it's really cool that we have Galen's Bardic as a tool, because behind the scenes, Bardic is kind of doing a lot of this recipe following and completeness combining for us. So we don't have to worry about it. But yes, word of warning to the wise.
Here we're showing our main results. So here we're plotting a comparison of different models using different data set. So the y-axis is just the planet frequency, and the x-axis is the semi-major axis. So the first panel is using all three data sets, the transit, RV, and direct imaging. The second panel is RV only, and the third and fourth are transit plus RV and transit plus imaging. So it is most obvious that using all three data sets can better help us to constrain the model parameters. And if you look at the left panel here, so using only the RV data will greatly underestimate the occurrence rate at closer distance, which is smaller semi-major axis, and it goes up forever at larger semi-major axis. This is kind of makes sense because we only have information of like intermediate semi-major axis, and we have no information about what is closer and further out there. On the right panel, we're using the transit plus imaging data, which means just no RV. And it is actually not dramatically failed the fitting, as we're only kind of missing the points at the peak. But this does overestimate the number of like planets kind of like in the middle, because it's kind of like where the slope of the model kind of transit to another.
All right, so now we're actually going to talk about all of the different parameters in the model that we're fitting and just kind of comparing how the different combinations of surveys affects those parameters. So like one of the parameters of the model is the actual overall occurrence rate of giant planets, which in the combination of all three surveys, you get around 45%. And then when you're using some combination that doesn't involve all three, it ends up being slightly higher than that. But really the big difference is just in terms of setting a strict upper limit, which when you don't have all three surveys, it can end up blowing up to all kinds of like really unreasonably high values. And then one of the other parameters is the power law slope B1, which is basically the slope of the distribution at small separations. And in all cases, as you're getting closer to the star, the separation or the occurrence of giant planets is going to go down. But what happens when you don't have the transit data is that it's basically entirely unconstrained and can especially blow up to really high values. And this is kind of obvious because if you don't have the transit data, which is what's probing the inner parts of these planetary systems, then you're just not really going to be able to say anything about what's going on at those close separations.
you're about to notice a theme. So for B2, it is the second power law parameter. It's for at larger separations. And what you may notice is that all of them show a decline at large separation. However, the transit in RVs is much closer to all three of them being combined. And the transit in imaging appears to go to a much steeper slope, while RVs a much more gentle decline. So basically, including versus not including the RVs is really important. The last parameter is our peak separation, which is where your power law breaks at. The best fit for all surveys combined is about 1.5 AU is where this power law turns over. No RVs will lead to a peak at much, much closer in separations. While no RVs, wait, did I say that right? RVs will lead to a much closer break. RVs will lead to a break at much closer separations, whereas not including them will make them peak at higher separations. That's how English works. And you can see that just the RVs and transiting together is very close to the original all three survey fit.
So what information can we draw from this that tells us about planet formation? So what we can see is that generally in the inner region within 1.5 AU, planet frequency is increasing with increasing distance away from the star. That's a very well documented trend. It turns over around 1.5 AU, which is generally around the snow line for a lot of these systems. And so that tells us that maybe it's once water has been able to solidify past that line, that provides a lot more source material for being able to build up larger planets. And perhaps your planet formation rate is then going to plateau because the amount of stuff available has sort of reached its maximum. And in the outer region, however, the picture is not exactly clear. Past 1.5 AU, radial velocity measurements would suggest that the planet frequency is decreasing. That's the pink points. But then the direct imaging data would maybe suggest that actually that planet formation frequency is flattening out. So which one is it? Well, you have to realize that there may be hidden variables here that we might, back to the cooking analogy, we might think we're making orange juice, but actually there's some apples in the mix. So really it's more of a fruit salad. And the one thing that you might think about is that directly imaged planets tend to be really bright and young planets. And so we're actually probing planets at different points in their evolution. And so maybe this is an evolutionary sequence. Maybe the intrinsic formation rate is actually flat past 1.5 AU, but then over time, those giant planets are migrating inwards. And so when you look at an older population like the RV measurements, that's why you see a declining abundance of planets at those larger distances. That's just one possible interpretation. There's many others out there, but it's just to point out the fact that when you're including different surveys, recognize that there's some hidden variables there that might be telling, might be mixing up the story that you're trying to tell.
So that leads to some conclusions. Like Ray was talking about, when we're using different surveys, we're also probing different evolutionary stages within a planet's life. It's not only just how we go about detecting them. There are also obviously inherent biases with each of these detecting methods. And so that tells us sort of what different populations we're probing. And so while they have all of these biases that are important to consider, you can have a better, more well-rounded view as to how best to model them if you include different surveys that are involving these different detection methods. And so if you were to ignore one survey from one detection method or just one survey in general, that can lead to your modeling efforts to be led astray a bit, and you would have to interpret a different kind of fit than you were if you were to include more. So if you go about it in a more homogeneous way by combining different data sources, like Bartik is doing, if you combine different surveys that consider different detection methods, then you can avoid incompleteness and issues with bias problems arising. So that's it. That's it for our group.
Okay. Yeah. Okay, so we're pretty sure on time, so we'll just skip straight to the feedback. Galen?
Sweet. Yeah, really cool stuff. I especially appreciate the violin plots and how you unpack different things. Just one point is that when you fit the broken power law to the radial velocity, you may have noticed that the break was like way closer in. So it wasn't fitting in the same regime. So that's a case where you maybe even like a triple broken power law or like something else would work. Or if you like truncated your priors, you could see where the RV placement in the right regime is because that's sort of like a different physical parameter you found. But otherwise, really cool stuff. Thank you.
Thank you.
All right, let's thank the first group again.
Okay. Do this first.
So our next two teams are presenting. They are remote. And I just want to, while we were switching to their video, I just want to say a big thank you to them because they are 12 and a half hours. Like they are having a 12 and a half hour time difference than us. So it's 3 or 4 a.m. for them right now. So really appreciate them staying up late, doing the project and presenting the result.
So, hello everyone, I'm Advay and I'm going to present today. Hello from the other side of the earth, since we are 12 hours ahead in time. Our team consisting of Aniruddha, Aritra, Subhash and me are going to present on how occurrence rates of giant exoplanets depend on the mass of the host star. Next one. We have taken Kepler data from Kepler's CLS SHINE survey data and divided into two groups based on their solar and masses as seen. To make sure our comparison is fair, we used inverse detection efficiency method, and in the end, we found that giant planets are more common and around higher mass stars, which agrees with findings from research studies that were provided. Next one. From segregated data, we see that it's clear indication of giant planets appearing more often near higher mass stars. If we had to find out detection rate for all the data provided, that is the planet to star ratio, we clearly see that the higher mass star perform much better in all the three surveys. The CLS data has the highest detection rate of 22.6%. And if we are comparing the detection rates combined, then it rises from 0.19% to 0.23% from the lower versus higher solar mass. Now, Aniruddha will do the next slides. Thank you.
Yeah, hello everyone. For my part, I have tried deriving the completeness maps, and it is seen that the completeness map works well for the CLS survey, showing a high completeness at intermediate mass and axis, and there is a sharp drop-off for the low mass, wide separation planets. Few planets fall in the low completeness zone, indicating likely survey bands. But for the Kepler survey, we see that the completeness region declines sharply beyond 1 AU. For illustrative purposes, we injected a synthetic completeness model to explore trends at a small semi-major axis not covered by the official Kepler maps. We modeled the completeness to be high for close-in orbits and to drop off sharply beyond 1 AU, mimicking Kepler's known detection limits. Most observed planets fall within the high completeness region. This synthetic map extends sensitivity below 0.5 AU, allowing fairer comparison with other surveys like CLS and SHINE. These are the same three plots for the CLS, the SHINE, and the Kepler survey, but for the high mass beam. And with this, I hand over to Subhash, who will be explaining the next slide.
Hello, everyone. My part is occurrence rate. Here we can see two plots. The left one is for lower mass stars and right one is for high mass stars. In lower mass, we can see that only Kepler and CLS detection is detected. And here in the higher mass, we can see Kepler and CLS and SHINE. In next, we combine these higher mass and lower mass one. And in the next line, okay. Here we combine this and we can see that in near 1 AU, there is a peak for all. Here, Shine has wider range, about 100 AU, near 100 AU. Next, in the next, we used fitted model. In our model, we used 10,000 steps and 32 walks and 2 chains for our sampling. By this, we can see that the higher mass has higher occurrence and lower mass has lower occurrence. By this, we can say that higher mass stars have higher occurrence of giant planets around it. Next will be
Thank you, Subhash. Now that we have modeled the data, this plot here compares the occurrence distribution of giant planets for both the stellar mass bins. As you can see, the orange one shows for the higher mass and the blue one is for the lower mass. The appearance of the shine data in case of the orange one constrains the data for the higher AU, while the more abundant availability of the Kepler data constrains it at the lower end of the AU for the blue lower mass case. Now in the next slide, if we go, these corner plots show how the posterior distribution of our model parameters of each mass bins perform. In the left panel, if you see, it is for the low mass stars and the right one is for the high mass stars. We have fit a broken power law to each of these, which allows us to capture both of the inner and outer region behaviors. You can see some correlation between the log break and the B1 and B2, mostly in case of the lower mass stars. This helps us to validate the sensitivity of our model to the changes of occurrence rates across different separations. In the next slide, I want to summarize what we did. We explored how the occurrence of giant planets depend on stellar masses using the data from Kepler, CLS, and SHINE. By dividing the stars into low and high mass bins, we saw a clear increase in planet frequency with the stellar mass. Kepler dominated the coverage, but had detection limits at wider limits, which were filled up by CLS and shines, especially at large separations. Overall, we can confirm that the giant planets are more common around the more massive stars, which strengthens the link between stellar mass and planet formation efficiency. At the end, I would like to thank you all for this opportunity. That's it. Thank you.
All right. Thank you. Galen, any feedback?
Yeah, first of all, thank you so much for being up in the middle of the night. I appreciate it. I think you started to touch on this, but you mentioned that in your blue model, which was like the lower mass bin, you have these really wide uncertainties at large separations because there's no shine information. But then you also highlighted that in the orange where you do have information, it's like a factor of 2 tighter as like constraints on what that occurrence would be, which is sort of the point of this. So great job highlighting that, and thanks for doing this.
All right. Let's thank group number 2 again. Okay. All right. So our next one will also be a remote presentation. Go ahead and take it away.
Sure. Hi everyone, my name is Shan. I am a senior majoring in ECE from India, and I'm here to co-present on the topic of exploring how different statistical models affect the way we interpret the data for higher mass detections. And Catherine, if you could go to the first slide. Yeah.
Yeah, sorry about that. All
No,
right, there we go.
Yeah. So what we are doing in this project is trying to understand what kind of biases are applied by what different functional forms we use. And next slide, please. And we have tried to use a couple of functional forms. We'll soon see why we chose this particular ones, at least some of them, because there are some physical interpretations that we assume to be true in them, and we'll see how each one of them works. Next slide, please. So first of all, we just took a regular polynomial function as a control model to see how, if we replace it and how it affects our model. And surprisingly, it gave quite relatively good results in terms of the occurrence rate compared to the other models. Next slide, please. So the log normal model is one of the ones that we use based on a physical interpretation of, say, for example, if you have a solar system like ours, then there is a certain perimeter around the host star, which would not be very conducive for a planet to form. And what we assume here is distance from the sun in terms of AUs. So if you replace the parameter mu here with say 0, then the whole term would collapse up to like the value of 1 AU because it's an exponent form. And the assumption here is that like any planet that forms and that is of interest to us would be at least 1 AU away from its host star. And there are other parameters where you can control the different weights. So for example, if you want to control like how much you want to prefer to have like high mass planets formation, then you can control the value alpha and so on. F naught is simply the sort of amount of planetary objects you want in your model. Next slide, please. In the step function, what we are assuming is that the formation of planets is not continuous and it is stratified. And surprisingly, it gave good results in the Kepler dataset. So here the logic is that whenever the planets are forming, due to tight competition between nearby planets, there are always bands of empty spaces in the protoplanetary disk. So that's why we chose this model to sort of understand how the distance between them would affect the planet formation. Next slide, please. We took the Gaussian mixture as it was a part of the question. It's not really much, there's not much of a physical interpretation behind this. Simply, we try to sort of model how, on an average, the planets are forming around a star and see how the results are. And it wasn't really able to grasp much of the occurrence rates. So yeah. Next slide, please. In the exponential function, what we are trying to model is that in general, like if you move away from a host star, then the amount of planets that are forming would decrease. And sort of we are using that decreasing exponential as our model to quantify how the occurrence rate would drop down as you go far away from the sun on the semi-major axis or the x-axis. Next slide, please. And now we'll see how the different models performed. And so, Catherine, if you can take over.
Sure, yeah. So now we're looking at our results from each of the different model fits. So this is the step prior. We have our corner plots on the left and our model fits on the right. So I believe this is the one that performed the best for the Kepler sample. Then the polynomial fit. Let's see, we don't have quite as many steps, so the resolution didn't turn out the best on the corner plot, but you can see fit on the right here for each of the different surveys. And then our log normal model. Our Gaussian, which did not work out quite so well. And then finally our exponential model, which ended up being the best of the ones that we tested. So in each column here, I just highlighted which fit had the lowest BIC value for each of these. So in all the surveys, beyond Kepler. We got the exponential models, the best fit. Though you can say we have pretty large error bars, so we would need a longer integration time to get better results. And then here were our occurrence rates for each model as well. So the Gaussian didn't turn out so well, but got percentages for each of the different models, and then the extrapolation only really worked out for the step function and the log normal. Yeah, and I think that's
Yeah,
we
and I
had.
just wanted to conclude with saying that we are still like this short time period was not enough to cover up the higher iteration numbers, and I think like if we increase the n steps, as we have seen from what we are doing, we would see better results. So we are just going to continue that.
All right.
Yeah.
All right, Galen.
Cool. This is a truly wild amount of models. I'm very impressed by how many things you tried to fit. I agree, I think, with the sentiment that like running things for longer may help you get some of those like convergence and not like dropping down to negative infinity in your occurrence rates. Another thing that could like be really useful when you do that is to put some more stringent priors into like your models. So like a prior that says your occurrence rate should not be, 0 at a certain point, or just make sure that you have like, I don't know, positive numbers. But otherwise, yeah, that was really interesting. I think there's also some like cautions for everyone here that like Bayesian information criteria aren't always like the perfect indicator. Like you had this exponential model that statistically says that it fits pretty well, but not like that much more than some of the other models that look better visually by eye. Yeah, like these are all on the order of like 250, 260. So just highlighting sort of difficulties of trying to argue which one is the best. But truly, thank you so much for trying all these different models. It's really cool to see.
Thank you so much, sir.
Yeah, so
thank you for
if I can just add, yeah, thank you very much. That was really nice to see all the models. One suggestion would be first to look, at the curve itself, and then try to find a model that more simply can fit these lines. For instance, using this broken power law, that would be helpful. Yeah. Thank you.
Thank you so much. Yeah, we'll try that.
All right, let's hear it for the two remote groups one more time. All right, next up is in-person team. And let me just ask, when each of you speak, go ahead and say your name and where you're from, and then go ahead and go into your pitch.
Okay, it's your group 4, right? Yeah. Share. That's step 2. There's a mic.
Is that working?
It's up
Oh,
just a second. Should be. And you can see it.
Okay, it looks like the clock is rolling. So, hi everyone. My name is Brandon Radzum. I'm a PhD student at Indiana University. So, our project is part of the session 2, or the hands-on session 2, which is all about astrometry with giant planets. And we did project number 3, which is the super fun one. So, just a little bit of background before we get into the details. The general motivation for this project is that, of course, a lot of the orbits we're tracing out for these really wide separation giants are pretty long in their baseline, and we're pretty limited in our ability to observe astrometric accelerations. So, of course, we want to know the mass of a perturbing companion, right? But it's pretty hard to do that, even statistically, with the baselines that we do have. And Guillermo Torres in 1999 published a really impressive paper kind of outlining how to derive statistically the mass distribution for a perturbing companion on a wide orbit from just the astrometric and radial velocity components of the star's acceleration. But not really the problem, but the challenge with Guillermo's result was that these relations are quite complicated. They're not shown here so as not to scare everyone away. But just trust me when I say that they're not very pretty. So the idea instead is to use a little bit of a more intuitive formalism that instead of relying on Kepler's laws and all these things that Torres did, we just think about Newton's laws of gravity, which has the acceleration in it, and think about the geometry of the problem. So with that, I guess I'll pass it off.
Hello, everyone. I'm Ricini Pereira. I'm a graduate student from State University of New York, University of New York at Albany. So I'll talk about the concepts that we used for our project. The long period companions to main sequence stars can induce accelerations. These accelerations could be along the line of sight or in the plane of the sky. So the accelerations along the line of sight, we call them RV accelerations or trends. And the accelerations in the plane of the sky, we call them astrometric accelerations. And the acceleration we can get by applying Newton's gravitational law to the star and the planet. The star-planet separation is r, and the angle is phi. Then we get gmb over r squared for the acceleration. And then taking the component along the line of sight, we get the RV acceleration. And then getting the vertical component, which includes sine phi, we get the astrometric acceleration. And then we look at the projected separation, which is the product of the distance from Earth to the star and the angle of separation rho. So d rho, we're going to approximate that to the vertical component of r, which is r sine phi. Then we use one of these equations together with the projected separation and Monte Carlo simulations to get a mass probability distribution for the companion, the star, and my friends will talk more.
Okay, thank you for a nice introduction. And my name is Jang Ho-bae from Seoul National University, and I'd like to introduce the procedure for estimating mass of the companion from astrometry and checking its distribution from Monte Carlo simulation. So we have to sample uniformly the cosine phi, not the phi itself, because what we exactly don't know is the radial velocity of the sky. When in our hand there is only the information from the astrometry. So following this equation, I uniformly sample the cosine phi, and when I convert it to the phi value using the arc cosine function, the distribution look like this. And following the equations in the previous slides, so I can change the r sine phi and d rho, and I plug it into here, and then we can obtain this equation. So, and the large phi corresponds to this, so inverse of the sine cube phi, and I calculate this through these pi's, and I can get this distribution. And when I get the median value is around 1.054. So next.
Hello, I'm Joshua Brumley. I'm a grad student at the University of Toronto. And so we can also to find an analytical description of this distribution. And by doing that, we found from the previous slide that this big phi is 1 over sine cubed of little phi, where little phi is the inclination angle. And using the chain rule and assuming that the distribution of inclinations is uniform in cosine space, then we get that the distribution goes as sine to the 5th power of the inclination over 3 times cosine. And so then you can either solve for the distribution in terms of big phi and you get this expression, or you can just plot this parametrically. Either way gives the same curve, and you see this curve matches the distribution well. And then from the, if we integrate the analytic solution to find where half the distribution under the curve is located, you get that point is of a big phi value of 1.539, which matches the Monte Carlo simulations that we performed.
All right. Hi, everyone. I'm Pranab Premnath. I'm a graduate student at UC Irvine, and I'll be talking about the next part, which was trying to derive the mass of the companion using a RV trend, radial velocity, if you didn't know that. I don't want to bore you with another derivation because we're low on time, and also it's 3:30. But we derived the mass of the companion to be that equation on the top, where A slab RV is that RV acceleration or the trend. And as we mentioned before, astrometric acceleration, we're looking at the plane of the sky. RV acceleration, we're looking at the line of sight. So there's that extra factor of cosine phi. Instead of a 1 over sine cube phi, it's a cosine phi in our function of that angle between the line of sight and the physical separation. And when we plot a histogram or our phi RV MC distribution, we can see that it decays as we increase phi, kind of like the attendance in this workshop today.
Nice. Okay, in the spirit of skipping more math, the fun thing to note is with if you take the inverse of this phi equation, you'll get a doubly valued solution. So even while part of this derivation, like this derivative up here is just a simple chain rule, the rest of the derivation, which the solution shown on the bottom right here, is a little more complicated because here we have a plot showing the big phi distribution as a function of this like orientation angle, and you can see some weird divergences happen at our bounds, which are correspond to 0 and pi over 2. So you have to, there are actually 2 regimes where your solution, your analytic solutions are valid, and they're split or bisected at 1 over root 3, and William will tell you more about this.
Yeah, so I'm Will Durock, I'm at UMD, and yeah, I mean, so this is already pretty ugly, but there's actually something kind of interesting and nuanced here that I think is worth highlighting, which is the fact that when you have a multi-valued function like this, and you have to try to compute a PDF, right, a probability distribution, which is ultimately what we're trying to do with 8 seconds left here. What you have to do is you have to divide it into subdomains, right? And then use basically conditional probability to say, what is the odds that I fall into one subdomain or the other? And then once I'm there, what is the actual PDF within each subdomain that you then sum together? And so the sort of funny thing is that sounds complicated and horrible, except that these factors cancel out in the long run. And so you end up just summing the 2 solutions over here, which is the end of the, okay, nope. So you sum these 2 things, and still ugly, but actually a lot simpler than you might expect, just from the what has to go into getting there. And yeah, so with that, I think since we're over, we'll conclude, and thank you.
All right, do we have some feedback for this group?
That's it. There. Now it's on? Okay. I think that's it. Really well done. That's exactly what I got. And if you go through the incredibly painful process of plugging things into the formula, yes, it's the same. So very well done.
All right, thank you to that group. And will the next group please come up? And just a reminder, as you come up to the microphone, make sure you say your name and where you're from, and then do your pitch.
Oops. There.
All right. Hi, everybody. We did the Gaia Astrometry Group Project 1. So really quick, we're all just going to introduce ourselves. So I'm Ashley. I'm a graduate student at LSU.
Gabe Weibel, I'm a graduate student at the University of Arizona.
I'm Henry. I'm going to my last year of undergrad at Amherst College.
I'm Emily. I'm a grad student at Louisiana State University.
I'm Claire Finley. I'm a grad student at UT Austin.
And I'm Catalina Zamora. I'm a grad student at UMass Amherst.
Okay, cool. Okay, so I'm actually going to pass the mic off.
Alrighty. So for anybody that was here during the hands-on session earlier this week, we started from the same Colab notebook. So a lot of these criteria that we used to identify accelerations and also try to reject some binaries remain the same, but we did make a few tweaks. So we throw out white dwarfs as best as they could be identified from the Gaia information. And the RUI and this IPD frac multi-peak help reduce the chances of binaries polluting these accelerating sources that we're really looking for substellar objects. We make a cut on the acceleration significance, and we were pretty lenient with a 2 sigma equivalent or greater. And from there, we're looking for substellar objects at resolvable separations that are very likely to be in young associations. And that gave us 53 targets, which was too many for us to vet manually. So we were further able to down select from comparing to the empirical Keck L prime contrast curve. And we got 6 nice targets, and there's 6 of us, so we could each investigate one of these in more detail. So we have the contrast curve, where anything above that line, we should be able to detect with similar observations. Anything below the line, we wouldn't be able to resolve. And these curves are tracing the predicted brightness of the companion to the star as a function of separation. And where they're leveling off is where we're hitting the edge of the ATMO 2020 grid, which was 78 to 79 Jupiter masses. So we're really would be hoping to catch one of these objects in its sloped region. So now we're going to go through our targets that we investigated. We did a lot of manual searching through other star catalogs and publications mentioning these sources, trying to identify visual binaries, spectroscopic binaries, potentially already discovered planets, to see which of these 6 are most interesting. And I'll start with my star here, HIP, and this phone number. It's sort of between the Pleiades and the Hyades, and it turns out this one is a binary star, a close visual binary that's been observed with spectral interferometry, and it can plausibly explain the acceleration. So this is a source that we removed.
Okay, this is another one of the sources that we looked at, which was its HIP ID was 1292, but it's more often referred to as the HD 1237 system. It's a binary system with the host star HD 1237A having a spectral type of G, and there was a later detected M dwarf companion HD 1237 capital B at a separation of about 68 AU. M4 spectral type. And the primary star, HD 1237A, hosts a planet which is called GJ 3021b. I don't know why they switched up the identifier, just making it more confusing. But it has a projected separation of about 0.49 AU, so very close in. This planet was discovered with RVs from Coralie in 2000, and it has an MP Sinai of 3.37 Jupiter masses. But the inclination is really highly unconstrained, so that it can't tell us too much about what the planetary mass might actually be. This system is around 400 million years old, so it fits our young age cut, and it resides in the southern constellation Hydrus. As you can see in this lovely picture on the right, the system was imaged by VLT NACO and also the CFHT, but that's not shown here. And these were actually the images that discovered the companion capital B, but they didn't recover the planet. But I would put in asterisks here that they thought they wouldn't be able to get anything that was less than 30 Jupiter masses with CFHT and less than 15 Jupiter masses with VLT NACO. So they kind of didn't expect to see the planet anyways, but this is the only like imaging that's already been done on this. So then just making a quick case for observing the system. We are not sure if the acceleration that we see in Hipparcos Gaia is caused by the planet GJ3021 or the binary companion HD1237b. It was also noted that the available Hipparcos data was not precise enough to show that a significant part of the planetary candidates, this was part of a survey, could be of stellar nature, or is it substellar? Anyways, there's need for follow-up, basically. Also at this projected separation of half an AU and at the distance of 17 parsecs, that gives an angular separation of 30 milliarcseconds, which would be very difficult, if not impossible, to directly image, even with the coronagraph. And this is what they're showing the sensitivity limits with VLT NACO. So yeah, that's basically the case for observing the system.
Okay, my target was HIP 15095. It's a K-star. It's 18 parsecs away. It has a chi-squared of 6.3, which is barely above our 2 sigma cut. There's no nearby stars in Gaia or Washington double stars, but it has been observed about 40 times with a bunch of spectrographs. And here are the HARPS RVs that I pulled from Google. And if you look really closely, and I'm not gonna bother, but if you look really closely, you could draw many lines there, but regardless what you do, it's going to be very close. And I put the power motions on the right, and if you look really closely, there's not a lot happening there. Basically, I would say this is not worth wasting some observing time on.
So the next target was HIP 30314. This is a G1 star at a distance of about 24 parsecs. There were radial velocity observations with HARPS, and they determined that there were 2 companions, one 3 AU away at 1.66 Jupiter masses, and the other one was 10 AU away with 1.4 Jupiter masses. It was previously observed with Sphere, but due to bad weather conditions, they could not find any of the candidates. So we decided that it should be worth observing again.
Okay, my assigned target was HIP 57507. It is a G6 star located about 57 parsecs away. In my searching, I was determined to be a single star, no detected companion with Gaia, WDS, or in the literature. So we're pretty confident it's not a visual or spectroscopic binary. And it has been observed with HARPS, Espresso, and I'm not going to try and pronounce that acronym. But it has a lot of spectra on it and some RV studies. But there's also no current confirmed exoplanet, so we decided that it should get added just to see if there was one, because it did pop up in our target list. And our last target. Thank you.
Okay, our last target is HIP 22738. We're running out of time, so I'm not going to waste your time. When I looked it up in SIMBAT, it called it a spectroscopic binary. The instructions said to get rid of those. But yeah, so in SIMBAT, it called it a spectroscopic binary, but it is classified as an M3 object about 90 parsecs away. And the final nail in the coffin was it is an entry in the WDS. So we just said no to that, guy. So this is our final target list.
Our final target list is these 3. We have some RV planets, one with no known companions, very exciting, and one that has an RV in a binary, but definitely worth a follow-up. Thank you all so much.
All right, Tim, Tim or Kyle?
I can just go up to the mic here. Great stuff. Wow, this is I was thinking while you were talking about that, I was kind of having flashbacks to when I was an early PhD student, just going through the targets. This is a really good demonstration of all of the different considerations that that you have to make when you're sort of deciding on these target lists for these precious 10-meter class facilities. So the one thing that I wanted to make sure that I noted, was sort of checking my notes on some of these stars as we were going, just to see if there was any kind of interesting things to add on. And one thing to highlight that's an additional consideration that you would not have had any reason to look at. Okay, so like this is not. I was looking at that HIP 57507, and so HIP 57507, it's identified as a candidate member of one of these young associations, which is, seems like a great, wonderful target. The one bit of caution is that its chromospheric activity is not what you would expect for a star with that spectral type. And so it's an important kind of example where when we're just selecting on targets that are sort of from these co-moving associations, sometimes you can have target or stars that are posing as young stars, at least for imaging stars from the ground. But really great job with all of this. This is just, it's really cool to see.
Great. Once again, when you got microphone, tell us who you are and where you're from.
Start introduce yourself and all the switchy slides. You want to introduce yourself?
Hi, I'm Maddie Scott, and I'm a second-year PhD student at the University of Birmingham in the UK.
I'm Matt Listowka. I just finished my second year as a PhD student at the University of Maryland.
I'm Allie Crisp. I'm a postdoc at Ohio State.
I'm Cole Smith. I'm going into my second year at UMD.
I'm Yulin Zhou. I'm a rising sophomore in a community college.
Hi, I'm Elena Adamson from the University of Birmingham in the UK, and I'm a first-year PhD student. So our project was investigating how giant planet occurrence rates change, or if they do change, with stellar mass. So just setting the scene a little bit. So we know that the evolution of a protoplanetary disk is influenced by the mass of its host star. So this will have direct consequences for the types of planets and probably how many planets are formed within that system. So from planet formation theories, it's expected that high mass stars will host giant gaseous planets, whereas around low mass stars, these are predicted to be kind of rare. But recently, there have been numerous discoveries of giant planets orbiting low mass stars, so this kind of calls planet formation theories into question. So what we're looking at is, do the expected trends in giant planet occurrence rates based on planet formation theories agree with our observations? So for this, we split our sample into 3 stellar mass bins. So we've defined low mass, mid mass, and high mass stars. So for low mass stars, these pretty much encapsulate all of the M dwarfs. So from 0.1 to 0.7 solar masses, mid mass is 0.7 to 1.3, and then high mass from 1.3 to 2.
So starting with the low mass bin, this fit did not go particularly well, primarily because there are not many planets in this sample. So there are only 3 Kepler planets out of the 9,000 stars, and 9 planets from the radial velocity survey, and no planets from the direct imaging survey. So we only have these sort of small semi-major axes, so our occurrence rates are very unconstrained at the high masses and very wide error bars just because of the small sample size.
For the mid-mass, we had a little more luck. We end up with 24 planets in the Kepler sample, 74 in the CLS sample, and still none in the SHINE sample, which wasn't necessarily surprising. But we ended up with a better constraint for this mass range and sort of matched up with what we expect from observations.
All right, and finally for the high mass star range, we can see that we actually do finally get to include SHINE stars as we get to those more higher mass stars that are going to have those like warmer hot Jupiters. But unfortunately, due to this also range, we've lost out on our radial velocity, so we've kind of snipped out the middle of the sample. And you can see that at the very beginning and at the very end, like the sample is relatively well constrained, but towards that middle, we get that large hump of they're actually having no radial velocity planets, so it's really hard to constrain there. And also the reason for why we chose the 2 solar mass like cutoff for like high masses is within these 3, within Bardic, there's actually like no additional planets if you go above 2 solar masses within like our planetary range. So we were kind of stuck in this like slightly lower mass range.
So we could see from the observational data, there's a significant dependence on stellar mass. And then giant planets are more commonly found around higher mass stars, which this trend is consistent with the core equation theory that suggests that both the mass and lifetime of protoplanetary disks play a crucial role in planets formation. Well, we could see there's a lot of uncertainties around the low mass star. This is because the Kepler's detection efficiency was optimized around like FGK type stars, which is as it's expected.
So just some final takeaways from what we found. The occurrence rates that we found pretty much were exactly what we'd expected. The higher the mass star, the more giant planets were present, apart from a slight outlier from our lowest mass bin. The occurrence rate was pretty similar to that of the higher mass stars, but it's mainly just due to the fact that there were almost no planets in that part of the sample. So yeah, that's what we found.
Great. Thank you very much for exploring this, especially the choice to try and look at like lower and higher mass stars. I have to apologize that I definitely cut some of those out of the tables so that file sizes would be smaller. So if you were to look at those full data sets, which will actually be in like the first release of this code, you'll be able to do a lot more, especially on the lower mass end. That said, the trends that you saw with the middle and higher mass bins aren't going to change, and the M-dwarfs will sort of fall in line with those. So maybe a good exploration of like how consistent these trends actually are across different populations. But yeah, thank you very much. Good stuff.
Also, just abusing my authority as chair, even though your total occurrence rate was a little unconstrained, your occurrence rate at 1 AU was very well constrained, and you could really see the trend there if you just zoom into the 1 AU parts. Okay, let's thank that team again. So why don't we have each of you introduce yourselves and tell us where you're from.
Is it on? Okay, it's on. Hi, I'm Sarah Stamer. I am a rising second-year PhD student at the University of New Mexico.
Hi, everyone. I'm Beatrice, a PhD student at Queen Mary University of London.
Hi, I am Akanksha. I am a postdoc from Institute of Astronomy, UNAM, Mexico.
So we are going to present our project on giant planet distribution dependence on stellar mass. Okay, so the criteria that we use to select giant planets from our data set that was made of CLS, SHINE, and Kepler survey are a mass range between 32 and 3,200 Hz masses for data from CLS and SHINE, and a radius range between 6 and 14 Hz radii for the Kepler data. And then we chose two stellar masses, two stellar mass ranges between, so a low mass range between 0.56 and 1.1 solar masses, and then a high mass range between 1.1 and 1.63 solar masses.
So once we applied all those criteria en masse to the stars we had, these are the stars and the giant plants we ended up with in our bin. So Kepler has a ton of stars just in general. There are no shine plants in the low mass bin, which you'll see later. That's kind of important, but there are all those numbers for you. So we'll start with the low mass stars. So we plotted the occurrence rate as this line right here as a function of semi-major axis. So you'll see it only really goes to like 10 AU, and that's because we don't really have any direct imaging stuff that goes out any further. And you can see it kind of just rises up and then it pretty much flattens out kind of around a few AU and then has a little bit of a dip back down. And okay, there we go. So we also did the like 2D plots as well to kind of look at the occurrence there. So you can kind of see most of the stuff's in this purple, blue, green range, which aren't super high occurrence percentages. Nothing around like 100 or some stuff around 10, not really. But CLS is kind of going in this middle orbital period bin, kind of around a day or so. And then Kepler's taken the stuff that's parts of days into hours. And then we also fit a broken power law to this. As you can see, it's very, very wide error bars over here. Kind of looks like it flattens out, but we don't actually know because, you know, our data has massive error bars and there's nothing really data-wise over here.
So unlike the low mass star, we have more planets or more outer planets through direct imaging SHINE survey. So this is the plot of giant planet occurrence rate around high mass stars. So, okay, so with the Kepler survey, as it can be seen in the figure, like as you go out to the towards from the, oops, sorry. Okay, so as you go out towards the semi-major axis, so the giant planet occurrence rate increases, and with the radial velocity survey, it kind of increasing and then little bit decreasing. But thanks to the SHINE survey, we get more data points and more planets, and now we can see like it's not further decreasing. And so yeah, so this is the distribution of 2D distribution of all the three surveys like Kepler, CLS, and SHINE. And this is our power law fitting for the giant planets around high mass stars. And like as you can see at the higher end, so planet occurrence is not decreasing.
So we kind of put them together just to see what would happen. So on the left here, all the high mass stars are kind of in blues and greens, and then everything else is in reds and oranges. Apologies if you're colorblind, and also it's kind of a busy plot. But you can kind of see both of those occurrence rates kind of together, or occurrence distributions. And then on the right, we plotted just the power laws. So blue over there is the low mass stars, and then orange is the high mass stars. So you can kind of see those massive error bars out here where we don't really have any direct imaging data for our small mass stars. So in conclusion, we found also, like the other groups, that giant planets are more common around higher mass stars. These F0 numbers are basically just the number of planets per star. So F0 is half a planet per star. Or if you want 1 planet per 2 stars, maybe that's a better way to think of it. And then F0, or for high mass stars, is about 1. So about 1 planet per star. The error bars are kind of high though, but you know, it works. There are no directly imaged planets in the low mass bin, so our slope of our power law far out there has a lot more uncertainty with it. And there are directly imaged planets in the high stellar mass bin, which gives us better constraints on our slope the further out we go in orbit. And with that, thanks to the organizers, the speakers, the hands-on leaders, the hands-on helpers, conference attendees, thanks for your attention.
Sweet. So also on par with expectations, I think. You had specifically brought up that like because you have so few or zero direct imaging planets at long separations in the low mass bin, that's like why things are so uncertain. One thing that could help with that is if you truncated where you are fitting your model to like an order of magnitude lower, like if you only have stuff out to 10 AU, you could stop there. Because that would also then help with some of your uncertainties on like the different free parameters. If you're not having to do a bunch of guesswork to imagine stuff where you can't see anything, then usually it helps to tighten things up. So just food for thought. But otherwise, good stuff. Thanks.
All right. Thank that group again. All right, can the next group come forward? All right.
It's faster.
All right, take it away.
Okay, hi everyone. We are presenting our group project. We also did the first project and the third question. So we're going to try and give you a different conclusion, but we were all asked the same question. So I am Rachel Hakmala. I'm a postdoc at Chapman University as of next week.
Hi, my name is Patrick McCreary. I'm a fourth year graduate student at Johns Hopkins University in Maryland.
Hi, this is Himanshu Verma. I'm a postdoc at LSU.
Hi, I'm Amy Glazier. I'm a recent PhD graduate from UNC Chapel Hill, and I'm now an assistant professor of physics and astronomy at Meredith College, also in North Carolina.
Hey, I'm Stephen Schmidt. I am a third year rising fourth year PhD student at Johns Hopkins University in Baltimore, Maryland.
Hi, everyone. I'm Dax Felice. I'm a postdoc at the Flatiron Institute. And to continue with the survey, as Rachel mentioned, we decided to do a different question for funsies purpose strictly. And the question we wanted to answer is, how does the giant planet distribution depend on stellar mass? So the mass bin of planetary masses that we decided to explore was 0.1 to 10 Jupiter masses. And then the other question we wanted to explore was, how does the small planet distribution change or depend on these two mass bins? So for that, we decided to look at planets with masses less than 6 Earth radii.
So I'm going to kind of rush through this, I guess, because we've seen this two other presentations. So this is for the smaller mass stars, so 0.56 to 1.1 solar masses. There's no directly imaged planets, so the SHINE survey had 0, which might tell you something about the occurrence rate of giant planets around smaller mass stars. Our model fit is meh at best, but you can see that in the middle where we have plenty of stars around 0.1 to 1 AU, the model is best constrained where those error bars are smaller, and then it becomes much larger where we don't have many data points. And then for the higher mass stars, we now can include some SHINE data, and the error bars on our model constrain a bit better. But we again see that at the very small and very large semi-major axes, our model kind of diverges in error bars. This is them overplotted with each other with some statistics on the number of planets and the number of stars that were in each bin, as well as the occurrence rates. And I guess, like I've kind of mentioned, the main comparison here is the fact that when you have, when you have data points on higher semi-major axes values, your model is going to constrain a bit better. And then the main takeaway that we've seen before is that around higher mass stars, you're going to find more giant planets. But also these error bars are very large. You can almost draw a straight line through it. So there's a weak relationship, but it does agree with literature to an extent.
Yeah, okay. So this is pretty much in line with what we've seen before based on like theoretical predictions for giant planet formation, where like in this citation on the left, they don't see as much giant planet formation around low mass stars. So anyways, one of the things that we wanted to do to extend this question was how the same occurrence rate deal works with rocky or otherwise small planets and how that is affected by stellar mass. So this is related to this citation on the right where they looked at the occurrence of small planets like sub-Neptunes and super-Earths around various different stellar mass types, just to see what's going on with that. So as it turns out, small planets are difficult. So I'll hand it off to Rachel to deal with this.
Yes, so that was a quote directly from Dr. Galen. He did approve us putting that in our slideshow. And basically what we found, which maybe you might have already guessed, but because we decided that small planet meant any exoplanet with a radius less than 6 Earth radii, we ended up clumping 2 different populations of planets into our model where we have the sub-Neptunes as well as the super-Earths. And you can, I'm gonna try. You can clearly see these 2 different populations in a few of these corner plots. And you can also kind of watch the model break in how we tried to fit it. And so essentially, we went in with very high confidence because when we plotted our graph looking at the semi-major axis versus the planet frequency, we saw these nice curves that we said, oh, those should be easy to fit. And what we did not consider was that we completely ignored the fact that the radii of the planet changes drastically. And so because the model assumes that the radii is relatively constant throughout the population, it really broke. But we had fun doing it, and that's all I have to say.
Yeah, so pretty much what we're seeing here is the radius gap for small planets. This was one of the big discoveries from the Kepler mission, just the idea that there are not just a continuum of small planets once you get out of the Jupiter and Saturn range. And in fact, there are 2 of them, that being the super-Earths and the sub-Neptunes. And there has been a lot of work following that up to see what is causing this radius gap that has occurred in the many years since Kepler first produced this interesting result. Anything else? I think not. So yeah, that's what we found. Small planets are hard. Thank you.
Yeah, small planets hard. So I'll focus on those. We've already talked about the occurrence radius distribution being like a nightmare that is not a straight line. So there are like there's a lot of discourse about like how do you actually fit that, and especially I think you were going down to like 0.1 Earth radii, which is like arguably outside the limits of Kepler. But in like the 1 to 6 regime, it's sort of also a broken power law. So if you were feeling particularly fancy, you could try that. I'll also say that like I think you talked about having 2 different populations. You arguably have 3 in that you have super Earths, sub-Neptunes, and then also like the real Neptunes in that like 4 to 6 Earth radius gap. And I think that's part of where that like you had a green line on your broken power law that was like basically straight out to like 0.1 AU, and that's sort of the largest of your population. So a hot mess, but you did a good job looking at it. So thank you very much.
All right, let's thank that group again. Will the next group come up? And I'm very glad to hear that you're having fun doing this. That's a part of this whole thing. In some sense, aren't the true exoplanet demographics the friends we meet along the way? So why don't you guys just go ahead and introduce yourself and where you come from?
All right.
Oh, actually, you can get started.
Okay, awesome. Hello, my name is Laura Chin, and I am a PhD student at Boston University. And I guess we'll just introduce ourselves as we go. Cool. Okay, I'll be giving the intro. So this is the broken power law item occurrence rates distribution that you've been seeing all along. We are picking up where we left off at the end of the workshop with Galen. And this will be a little similar to the presentation you saw earlier that Catherine and Sean presented, but we took a slightly different approach, so it's not totally the same. Instead of investigating a variety of different models, model shapes, we decided to put all of our blood, sweat, and tears into just one. And that one is the Gaussian distribution. So we've got our data set in the top corner over there. And this is the just Gaussian distribution we'll be using. You will notice, eagle-eyed viewers, that this is a log-log plot. So to accommodate for that, we will be using just kind of popping in a log right there over the X. And take it away about the free parameters.
Hey, what's up, guys? My name is Charles. I'm from the University of Arkansas. So I just want to talk to you guys about our methodology. All right. And so like my presenter or my project mate was saying that like it's just a pretty simple. We thought it was pretty simple going in, and it's just one model. And so essentially what we did, we just took Monday's Google Colab notebook, modified it. We took out the broken power law and we replaced it with our log natural distribution in order to shape, our occurrence rates. And so we have new free parameters. We got the standard deviation, the mean. These are all from the log normal distribution. And then the F naught, that's our scaling factor for our total occurrence rates. And then we just went ahead and modified our function, our prior function. And just a reminder, this is, with the data that we got from the notebook. And so this is like the planetary orbital separation versus the occurrence rates. And so just like any model, I think the best part of this was, for our priors, determining what our priors are, especially when you don't have any literature and you've never seen this before. And so, like I said, ideally what we want is that given the data, how well does our free parameters, represent this and that in our log Gaussian distribution, right? And so using MCMC, we did our steps for our sampling. We took about 16 walks. And one thing I will say about the steps, for this project, it did matter. If you wanted to make the process or the model go faster by reducing the step size, it's not gonna do well. And then for our walk, we reduced it from 32 to 16 to help with the process because it did take a while. And then we had 2 draws. All right, I'm handing it off.
Awesome. All right, howdy y'all. I'm David Shaw. I'm a PhD student at the University of Notre Dame. Let's see if I can figure out how to go forward. There we go. Awesome. So up in the top right, I've got our model again, just to remind us of the expression and what our free parameters are, how they all fit together. And here on the left, main feature is the data of the planet frequency from the Kepler, CLS, and SHINE datasets. And overplotted there is our model's best fits. Coming out of our MC analysis, like Charles said, we picked a reasonable number of steps for our analysis, which basically is just a nice way of saying Google Colab was giving us fits. So we lowered it until we got some kind of corner plot to show up. So you can see our best parameter fits here with the median value from the posterior, as well as some 1 sigma deviations there based on percentiles. So the overall sort of occurrence coefficient, F naught, we got about 50% or 0.5. Mu and sigma here, these numbers directly probably won't really mean anything to you. We're working on log AU. You can see that the data has a peak in the occurrence around a few AU, order 1 AU. But our Gaussian prefers a slightly larger distance for the peak occurrence. And yeah, so that peak in our fit is occurring around 15 AU. Yeah, I think I'll stop there.
Hello, Shashir Dalakia from the University of Southern Queensland. I'm also a PhD student. Yeah, so now we can do the fun thing, which is model comparison. So you've probably seen a lot of broken power law fits by now. We've done a Gaussian. What we want to do is compare the models, and we can't just compare the likelihood values or the goodness of fit metrics, because the models can have different numbers of parameters, and you could, of course, a model with more parameters is always going to fit better. So we use something called the Bayesian information criterion, which penalizes a model for having more parameters. So you want to make sure the goodness of fit is good enough to justify the extra model complexity. And when we do that, we actually get a lower Bayesian information criterion for the Gaussian fit than the broken power law. So we can say that the Gaussian model is more parsimonious. And we've plotted the two models up here. And yeah, now we can go bother the theorists to try and figure out why that might be. Yeah, I think that's it for us. Thanks.
Sweet. Yeah, I appreciate this. Like, I don't think I've ever actually looked at the power law next to the Gaussian on the same plot, so this is cool. You had made some comments about like there being visually a peak in these like inverse detection efficiency method points circa like 1 AU, but your model finding something at like 10. And to make things a step more complicated, if you translate your like median of the Gaussian, it's like somewhere in between those two, which I think speaks to like sometimes your free parameters and the visuals of the models you get are convolved when you like do things as a distribution in like the MC simulation space. So worrying about all of those is always important, and that's not always something that gets captured in like an information criteria metric. So here you have a Gaussian model that is like slightly more preferred compared to a broken power law, but arguably the broken power law visually maybe matches better. So again, I think I've said this like 8 times today, but like this underscores that you need a bunch of different metrics, a bunch of different qualification criteria to deem like which of your models is the best, even if one metric is preferred in a particular case like this is. So thank you very much. Good stuff.
Thanks.
Change groups here.
10. It's a PDF. Bring it over here. Page always the same thing. And full screen.
Hi, hello everyone. I'm Manon Lizana, a PhD student from IPAG in France, and I worked in the project number 1 for the session number 2, and in fact we were only 2 in the team, and I was with Paul Smith. Okay. So let's begin. I think that the main question we tried to answer was how can astrometry be used to identify the best targets for imaging exoplanets or brown dwarfs with the JWST. And especially in the JWST, you have 2 instruments for imaging with the coronagraphic mode, which are NIRCam and MIRI. Okay, so the goal was to build a short list of the target that we can observe. We started from the Hipparcos Gaia catalog of acceleration, and we calculate, first of all, the acceleration thanks to the second law of Newton. In fact, the acceleration is the variation in proper motion between Hipparchus and Gaia. And if you have this acceleration with an assumption on the separation between the star and the companion, you can try to calculate. Yes, so you calculate. Yes, I'm too fast. First of all, you calculate the acceleration, and thanks to this acceleration, you can estimate the mass of the companion. Okay, and so we have a list of targets, and we keep only the ones who meet, which meet these 4 requirements. The first requirement is that the chi-square is bigger than 11.8. The chi-square, in fact, is the deviation of the Hipparchus-Gaia catalog of acceleration from a constant proper motion model. Okay, so if the chi-square is I, that means there is a high acceleration. That means the proper motion change. That means maybe there is a companion. Okay, this second criterion was the companion mass is lower than 70 Jupiter mass. This is just because we want to avoid binary stars. We want to find exoplanets. Then we had a filter to remove brown dwarf because we want to focus on the main sequence. And we had some filters to avoid multiple systems. And then for instruments, for example, MIRI and the GWST, you can calculate a typical contrast curve. And we used this contrast curve to estimate the contrast for each of the stars in the target list. Finally, we add several stars, and we didn't have enough time to study all of them. So we had to choose a cutoff in mass and in contrast to have a short list. This is our results. In fact, we add all of these stars in blue. And because of the cutoff in contrast and in mass, we arrived with only 4 stars to study. This is the red ones. Those 4 stars are the one here in this table. And so we are going to investigate this 4 star to understand if there is a good target in these 4 stars. Okay, so the first one, I begin from the end. The first one is this one, and we think that this is not a good target because it has already been observed many times with many different instruments by the GWST, and there is already 1 planet found in this system. The second target with this one, and we think that this is not a good target because in fact the chi-square is really low. The threshold was at 11.8, so that means maybe because of the error bars, the acceleration is not so big, so maybe there is no companion, maybe the proper motion is constant. And also there is a common proper motion star, so I don't know exactly what does it mean, but this may be a binary star not detected. The third target was this one, and this is not a good target because in fact this is a complex system with at least 4 stars. So this is too complex. We think that we're not able to find a planet here. And the last target is this one, and we think that that can be a good target because in fact the chi-square is really high and it has never been observed by the GWST, but we have a lot of information about this star because it has been already observed by ground telescopes like Gemini, the Keck Observatory, or the VLTI. So we think that this is a good target, so let's observe it. Thank you for your attention.
Yeah, really great presentation, and kind of it's really complementary too to the presentation from the other group, focusing on stuff that can be observed from the ground. right? Because with JWST, suddenly you're able to access older planets. The one thing I wanted to point out among these different targets is that so the first HIP or the first target that you talked about, HIP 108870, is EPS Indy, right? You know, if it was, you know, a few cycles ago and you were sort of thinking about proposals for cycle 1, it would have been the first target on your list to image this, you know, this first older exoplanet. So really exciting stuff.
One small thing I will add is that if you have a common proper motion star, one thing you can do is you can see what the change of proper motion is. It's actually a vector. You can see if it points toward that common proper motion star. And
Yes.
if it does, that's the answer.
Yeah, thank you.
All right, we have one more group left. And as each of you come up to the mic, go ahead, give your name and where you're from.
Okay. Hello, everyone. My name is Karina Kimani Stewart. I'm a first-year grad student at Georgia State.
I'm Malia Rem. I'm an upcoming third-year grad student at the University of Kansas.
I'm Alex Howe. I'm a co-op scientist at Catholic University / NASA Goddard.
Okay, so our group took on the project of investigating the occurrence rates when you combine different surveys together. But before I get too far, I do want to acknowledge the contributions made by some of our teammates who couldn't be here today. I want to thank Marie Tagliava from Notre Dame, I believe, and then Disha Chakraborty, I'm so sorry if I butchered those names, from University of Kansas. So those are our other teammates. But yes, so we wanted to look at, if you combine different surveys, what pieces of the puzzle are you going to get and how does that change your occurrence rates? And so specifically, we combined the SHINE survey, the CLS survey, and then also Kepler. And so we've been hearing all week about how whenever you combine, you know, this survey and that survey and that survey together, you get different pieces of the puzzle because they have their own biases and they give you all sorts of information in their own. And so how do your occurrence rates change with that? So a couple of disclaimers before we get going. I want to note that for the CLS survey, we see that there's a bit of exclusion in the fit. Anything closer than 0.2 AU separation has been excluded. It's the fit has a hard time down to those really close separations, and it makes it really muddy when we try to plot it. So that's been excluded. So when Malia gets into that plot, don't panic. That part of the plot is just missing. And then also, I want to highlight that the fits will depend partially on the binning. So your planets will fall into different bins depending on how you bin whenever you do your fits. So just keep that in mind as we move through this. But yes, so for our combinations of surveys, we have 3.5 combinations. We have the transits in RV and imaging, so the trifecta together. We also have transits and imaging, transits in RV, and then just solely RV.
All right, so you can see in the top left corner, this is our occurrence distribution for our combination of all three of our surveys. So this is for Kepler, the CLS RV survey, and for SHINE, as you've seen already this week with its fitted model. And then the bottom left plot in the left corner shows the combined occurrence distribution for the Kepler and CLS survey. You can see here that below 10 AU, we get a pretty good fit for the fitted model. But of course, beyond that, the contour starts to look a little bit broader. And that's, of course, because we don't have our imaging data right there. And then next in the top right corner, we have our plot for the Kepler and SHINE data only. And you can see that there's a pretty good fit here as well, even with the RV data missing in the middle. We also saw that peak in the distribution that other groups were finding too. And then also, as Karina said, for the RVs only, we can see that the shape is different because, of course, the bins change with our change in the range of separations that we chose. So that's why you see like a lower planet frequency for those last couple of bins there. And then this plot is actually thanks to Marie, our member from Notre Dame, who could not be here today. She went ahead and she plotted the models for all of our surveys onto one. So the red contour shows our model for the transit and RV surveys, the blue for the transit and imaging, yellow for RV, and the black for all three surveys. And then she also plotted the distances at which each power law breaks for each of them. So we can see that for the transit and imaging survey, the power law breaks at the furthest distance, which is at 2.8 AU. And the RV survey showed a power law break at the shortest distance, which was at 0.4 AU.
Now, talking about which pieces of the puzzle do you have, if you look at the top line, what is the occurrence rate? You can compare the control of all three surveys against our three test cases, and all three test cases underpredict the total occurrence rate, which is modeled at about 69% of stars on average for all three surveys. Transits and imaging gets the closest, but it's still underpredicting, and that says if you're not covering all three surveys and the range of separations they cover, then you are probably missing some planets and maybe also missing some of the physics, because different physics governs different separations. And so I just have a few takeaways that we came up with. First off, RVs alone are a poor fit to the population as a whole, and that's not all that surprising because it's covering the narrowest range of separations. But also, as I said about the physics, the RVs are mainly probing places where planets would form in situ, whereas transits, for example, are covering separations where we think they would be migrating to. So it's probing different physics there. Transits and imaging together give a surprisingly good fit to the population as a whole, even though the peak is missing from the data in that case, although the uncertainties are larger, of course. Transits plus RVs also give a very good fit. That's less surprising because we're omitting imaging, which is the smallest data set. And our final takeaway, I wrote this here and I should have been more succinct. Our final takeaway is really beware extrapolation. Because a well-chosen model will give you at least a decent fit within the range of your data. It even does okay interpolating across gaps, but if you try to go outside the range of your data, you're going to have a hard time. Anything else?
Sweet. I think I'm going to put beware extrapolation on my tombstone. Yeah, so really cool stuff. And I agree with pretty much all of your like takeaways and interpretations of these. I have maybe 2 clarification points I can offer. Towards the start, I think we talked about like how you had a comment about like how the binning of the sample somewhat impacts the model, which I'll correct as not being quite true. Despite always putting them on the same plot, the like binned inverse detection efficiency points and the models are actually completely separate calculations. They never see each other. So the sort of draw of modeling in that case is that it is bin agnostic. The other thing is that on your slide comparing the different models, when you had this like RV only thing, there was a sort of like you had this break that happened much earlier in, which I think for a previous group I said was like you could fix that with priors. But in your uncertainties, there was actually a chance that the break was like at or near 1 AU. And then in that case, you do see that sort of downward trend from the power law, just not as common within the uncertainties. So those are just like other observations that I think fall in line with the conclusions you have here. So really good stuff. Thanks.
Thank you. One other fun thing, Chaz and I were just laughing because when you were making that comment about extrapolating, you know, the direct imaging community spent a decade submitting observing proposals saying how many giant planets we're going to discover and characterize from extrapolating RV surveys. It went amazing. So be it, yeah.
All right, let's thank that group again. Let's actually thank all the groups for some really amazing presentations.